Can everybody hear me? Where does knowledge come from? Until recently, it came from just three sources. The first one is evolution. That's the knowledge that's encoded in your genes. The second one is experience, the knowledge that's encoded in your neurons. And the third one is culture, the knowledge that you acquire by, reading books, talking with other people, and so on. But in just the last few decades, a new source of knowledge has appeared on the planet, and that's computers. And notice that each of these sources of knowledge was a major, development in the history of life on Earth. Evolution is life itself. Experience is what distinguishes, mammals from insects. And culture is what makes, humans so unique and so successful. And, the appearance of computers as a source of knowledge, I believe, is going to be every bit as momentous as the previous ones. Notice also that each of these sources works orders of magnitudes faster than the previous ones and generates orders of magnitude more knowledge. And computers are going to be no exception. In fact, Yann LeCun, who's the director of AI research at Facebook, says that most of the knowledge in the world in the future is going to be extracted by machines and will reside in machines. So how do computers discover new knowledge? Well, there's five main ways. One is by filling in gaps in the existing knowledge, a little bit like scientists at work. Another one is by emulating the brain, a very popular one these days. Another one is to simulate evolution. Then you can discover new knowledge by systematically reducing your uncertainty. And finally, you can discover new knowledge by reasoning by analogy, by noticing similarities between the old and the new. And the field of computer science that deals with discovering new knowledge is called machine learning. It's machines learning. It's the field that I work in. And one of the things that makes it not just very important these days, but also very fun and very fascinating is that every one of these paradigms of machine learning has its roots in a different field of knowledge. And it also has what I call its master algorithm. A master algorithm is an algorithm that you can use in principle to discover any knowledge from data. You take the same algorithm, you give it data from a different problem, and it learns to do different things, okay, which is very different from having to program computers, which is what the old way of doing things was. So the first tribe that we're going to look at is the symbolists. They're the ones who discover new knowledge by trying to fill in gaps in your existing knowledge. They have their roots in logic, in philosophy, and in computer science. And their master algorithm is inverse deduction, and we're going to see very shortly what that is. Then there's the connectionists, whose idea is to reverse engineer the brain, and therefore their roots are mainly neuroscience. Their master algorithm is backpropagation. The evolutionaries have their origins, of course, in evolutionary biology, and their master algorithm is genetic programming. Bayesians come from statistics, and what they do is essentially probabilistic inference. And then finally, the analogizers, they actually have their roots in many different fields, but the main one is probably psychology. There's a lot of evidence that human beings reason by analogy, and their master algorithm is kernel machines. So let's start with the symbolists. Here are some of the most prominent symbolists in the world: Tom Mitchell at Carnegie Mellon, Steve Muggleton in the UK, Ross Quinlan in Australia. And the basic idea of the symbolists is actually very simple, but also very insightful. It's this idea that learning is induction, right? And the induction is discovering general rules from specific facts, which is the opposite of deduction, which is going which is applying those general rules to infer specific facts. So in a way, induction and deduction are the inverses of each other, in the same way that, say, addition and subtraction are inverses. So for example, addition gives us the answer to the question, if I add 2 plus 2, what do I get? Well, 4. Subtraction is the answer to the inverse question. What do I need to add to 2 in order to get 4? And the answer is 2. Well, so the idea of induction as the inverse of deduction works in the same way. So for example, deduction is something like, if I know that Socrates is human, and I knew that humans are mortal, what can I infer? Well, I can infer that Socrates is mortal. Now, induction is the inverse of that. It's saying, like, if I know that Socrates is human, what else do I need to know in order to infer that he's mortal? And the answer, of course, is that humans are mortal. And once I know that, once I've discovered that rule, I can add it to my knowledge base. And then in the future, I can combine it in many different ways with different rules to answer questions that maybe I didn't even think of before. And as I mentioned, this is a little bit like scientists at work. And in fact, one of the most interesting applications of this type of machine learning so far is the biologist that you see in this picture. The biologist in this picture is actually not the guy in the lab coat. The guy in the lab coat is actually a machine learning researcher by the name of Ross King. The biologist is that machine there. It's a complete robot scientist that starts with basic knowledge of molecular biology, DNA, proteins, and so on. And then it looks at data. It formulates hypotheses to explain that data using inverse deduction. It designs and carries out the experiments to test those hypotheses using, DNA, microarrays, and so on, which is what you see there, and so on. And that robot is called Eve, and 2 years ago, it discovered a new malaria drug. And once you have a robot like that, there's nothing keeping you from making 1 million. So now we can make progress in science much, much faster than we could before. Now the connectionists, they're skeptical of this approach. They say it's too clean, it's too logical, it's too abstract, too high level. The best way to learn is to emulate the best learning system in the universe, namely the one inside your skull. So their idea is to reverse engineer the brain, to do learning that's inspired by our knowledge of how the brain works. The leader of the connectionists is Jeff Hinton. He started off as a psychologist. These days, he's more of a computer scientist, and he splits his time between Google and the University of Toronto. And he believes that the way our brains work, the way our brains learn, can be captured by a single algorithm. And he's been trying to discover that algorithm for 40 years now. In fact, he tells this story of coming home one day from work very excited, saying, "Yay, I did it. I figured out how the brain works." And his daughter replied, "Oh, Dad, not again." But, so his quest has had its ups and downs, but it's starting to pay off. In particular, this algorithm that he co-invented called back propagation is taking the world by storm. It's used for just about everything these days. The cell phone in your pocket probably uses deep learning in order to understand what you say, to do speech recognition, for example. Search results, ad placement, image recognition, all this is being done using the algorithms that he and others invented. Like, for example, people like Yann LeCun and Yoshua Bengio. So what's the idea here? We know that your brain is made of neurons. It's a big network of neurons. So what we're going to do is we're going to build a mathematical model of how a neuron works, and then we're going to connect those neurons in a network and try to make it learn the same way that your brain learns. And the key idea here is that all the knowledge that you have, everything that you know, everything that you've ever learned is encoded in the connections between your neurons, which is why this school is called connectionism. So we're going to do the same thing here. So here's a picture of a neuron. There's the cell body. A neuron looks like a little bit like a microscopic tree. There's a trunk called the axon. There's the branches called dendrites. The roots are also called dendrites, and then the roots of one neuron, the branches of one neuron connects with the roots of others, and the electric discharges flow across. So an electric discharge across the axon is called an action potential. And if the charge coming into a neuron exceeds a certain threshold, then the neuron fires. This is actually what's happening in your brain right now. There's this symphony of electric discharges going on. And the key thing is that, one neuron can be more or less effective at making another one fire. Some connections are stronger. And you learn by making those connections stronger or weaker. Okay? So we build a mathematical model of that. It's straightforward. You notice how there's a correspondence between the parts of this cell and the parts of this diagram. Here's my cell body. The inputs come in. They could be pixels, for example, in an image that you're looking at, or they could be other neurons. Each one of those gets multiplied by the weight. That's what we're going to learn. And then if that's sum, and then they all get added up, and if that exceeds a threshold, then the neuron fires. So, for example, if you're looking at a cat and you do recognize a cat, then the neuron fires. Okay. Now, the interesting question is what do we do when we have a big network of these all connected together? If you think about it, think of one little neuron in the middle of your brain. How is that neuron responsible for the mistakes or the good calls that you make? Right? This is often called the credit assignment problem, or maybe it should be called the blame assignment problem, because it's the question of what to change when something is going wrong. Okay? If it should be firing because it's seeing a cat, but it's not firing, then how do I need to change the weights? And that's where this very famous algorithm called backpropagation comes in. What backpropagation does is essentially just looking at each one of those weights in turn, starting at the output and going all the way back to the input and saying, if I change this, if I increase this weight a little bit, does the output become closer to what it should be or farther? And then it changes all of the weights, and then it looks at the next example, another cat or maybe another dog, and keeps going that way. And as I mentioned, this type of learning is used for just about everything these days, but perhaps the most famous example is one that was on the front page of the New York Times a couple of years ago. And it became known as the Google Cat Network. In fact, this network can recognize all sorts of things besides cats. But the journalists picked up on the cats because this network was learned from YouTube videos, right? What they had was the network watching hours and hours and hours of YouTube videos. So maybe it should have been called the Couch Potato Network. But they call it the Cat Network because, I don't know if you know this, but people love to upload videos of their cats. So there's more footage of cats on YouTube than anything else. So the single thing that the network did best was recognize cats. But it recognized a lot of other things as well, and you've been using it when you use Google, probably without knowing it. Now, the evolutionaries, they say, well, sure, backprop is nice for, fine-tuning the connections between your neurons. But it was evolution that actually produced your brain in the first place, not to mention all of life on Earth. So maybe the best way to learn is to simulate evolution on a computer, except that instead of evolving, plants and animals, we're going to evolve programs. So the first person to run with this idea was John Holland. And then, more recently, people like John Coase and Hod Lipson have done a lot of work in this field. So here's the idea. We know roughly how evolution works. So we're just going to make the computer do the same. We're going to have a population of programs, each of which has a genome, which, of course, is not going to be DNA-based, but it's just going to be bits, right? So in a computer, a genome is really a bunch of bits. The bits define a program, and then that program runs on the task and gets a score for how well it does, called the fitness, by analogy with biology. And then the fittest programs actually get to mate. You actually generate children programs by crossover between the genomes of two parent programs. And then they get randomly mutated, and then you have a new generation of programs. And the amazing thing is that starting from random bit strings, the evolutionaries have been able to develop things like radios and amplifiers, better in many cases than the ones that were designed by human engineers. In fact, these algorithms have actually, they have a lot of patents. Literally, they've won patents for the things that they've produced. Now, John Coase's idea was to say, well, if what we're trying to do is evolve programs, bit strings are a little bit too low level. Let's actually just evolve the actual program trees, right? A program is just a tree of subroutine calls all the way down to simple things like additions and multiplications. So let's actually have trees representing the programs, and then we pick a random node in each of the tree to do the crossover. And then we swap the subtrees and evolve new programs that way. So for example, here, if you pick this point as the crossover point, one of the trees that you get is the one in white. And that tree is actually one of Keplers Laws. That tree represents one of Keplers Laws, which is the one that gives the duration of a program's of a planet's year as a function of its distance from the sun. Okay, and this is very easy for these genetic algorithms to evolve, and they do much more complicated things as well. For example, these days people like Hod Lipson are actually busy evolving not just programs anymore, but real hardware robots. So this spider that you see here is an actual robotic spider from Hod Lipson's lab. And the way it works is they start out with random parts of piles in simulation. once the robot in simulation is competent enough, it actually gets 3D printed. And then the robots start moving around flying. They've also evolved dragonflies for, dragonfly-like robots, for example. And then in each generation, the fittest robots get to program the 3D printers to produce the next generation. This is happening right now. It's very exciting, maybe also a little bit scary, right? So if Terminator ever comes to pass, maybe this is how it's going to come about. Okay. Now the Bayesians, they are known in machine learning as the most fanatical of the 5 tribes. And the reason for that is that they used to be a persecuted minority in statistics, but, so they had to become very, fanatical in order to survive, and it's a good thing they did because they have a lot to contribute. So here are some of the more famous ones: David Eckerman, Huda Pearl, Mike Jordan. And the Bayesian learning is all about something called Bayes' theorem. Bayes' theorem is one simple rule for updating your beliefs with new evidence. And Bayesians love Bayes' theorem so much that there was this Bayesian machine learning startup that actually had a neon sign, a huge neon sign of Bayes' theorem made and hung outside their office for everybody to see. So what does Bayes' theorem say? Bayes' theorem actually is just the following idea. I'm never sure of my knowledge when it's learned from data, right? I'm always uncertain. So I have to quantify that uncertainty using probability. And then what I do is I start out with my prior probability that each hypothesis is true. That's the prior right there. And then what happens is that as I see evidence, the hypotheses that are consistent with the evidence become more likely, and the ones that are inconsistent become less likely. That part is called the likelihood. And the product of the two is the posterior, which is how much I believe in each hypothesis after I have seen the evidence. And hopefully, as I see more and more evidence, some hypotheses eventually become, hopefully eventually one hypothesis becomes the clear winner, but that's not necessarily the case. Okay? And there's also something called the marginal, which just ensures that the probabilities add up to 1, and we didn't worry too much about. And again, Bayesian learning is used for all sorts of things these days. Your first self-driving car will probably have, a Bayesian learning system inside it. One application that we're all familiar with is spam filters. So in spam filtering, the two hypotheses that you're looking at is this email is spam versus this email is good. And then the evidence is the content of the email. So for example, if the email contains the word free in all capitals, that makes it more likely to be spam. If it contains the word Viagra, that makes it even more likely to be spam. And if it contains free Viagra 4 exclamation marks, it's almost certain to be spam. On the other hand, if it contains the name of your best friend on the signature line, that makes it less likely to be spam. And these days, people use all sorts of different algorithms to do spam filtering, but the first one, and still of the best and most widely used, is Bayesian learning. Now, finally, the analogizers. This is actually a lot of people, that I've met that have read the book. They say, this is what I do. I reason like this. I'm an analogizer. So what do the analogizers do? The idea of the analogizers is that everything that you do, everything that you learn, is reasoning by analogy. And probably the most famous analogizer is Vladimir Vapnik. Another one is Peter Hart. Douglas Hofstadter, which you may know as the author of Gödel, Escherbach, and other books, he actually coined the term analogizer. And his most recent book is 500 pages arguing that everything about learning, everything about intelligence, everything we do is just reasoning by analogy. So what's the idea here? It's actually an incredibly simple yet extremely powerful idea. Let me illustrate it by means of a puzzle. Suppose I gave you a piece of paper that's a map. And what I've marked on that piece of paper is the locations of the cities in this one country. I'm calling it Pozistan because it's the pluses. And another one, which are the minus signs, are the cities in Negapolis. So in Nagaland. Okay, and what I ask you is, knowing just where the cities are, tell me where the border between the countries is. Okay, now of course you can't do that because the cities don't determine the border, but you can roughly guess where the border might be. And the simplest analogy-based algorithm, it's called nearest neighbor, just uses the following heuristic. It says a point on the map is in Pozistan if it's closer to a positive city than to any negative one, and vice versa. So for example, when this type of learning is used for medical diagnosis, something that it's very good at, what happens is like, I'm a doctor, I see a new patient. What I do is I look in my files for the patient with the most similar symptoms. And then I assume that the diagnosis is the same. And this may seem very simple-minded, but there's actually a theorem that proves that if you give this algorithm enough data, it can learn, basically anything. Now, there's a couple of limitations of this. One is that that boundary is a little bit jagged. It's probably, the real one is probably a little bit smoother. And also, we're remembering here a lot of these examples, a lot of these cities that are actually not necessary. If, for example, this city disappeared, its neighborhood would be absorbed by these other cities, and the boundary would actually stay the same. So I could actually throw this away and that away, and nothing would change. Which here doesn't seem like a big deal, but on in these days of big data, that could be a huge amount of memory and a huge amount of time to try them out. So support vector machines or kernel machines, this is Vladimir Vapnik's invention. This is one of the most powerful kinds of machine learning there is. What they do is they solve both of these problems. The support vectors are basically the examples that you need to remember because they support the frontier. If you take one of those out, then the definition of the concept changes. And the way they do this is by, trying to draw a line that has all the positives on one side, for example, all the cats on one side, and all the negatives, for example, all the non-cats on the other side, while keeping as far away as possible from each of them. Trying to, maximize what's called your margin of safety. Imagine that these were landmines and you needed to walk between them, right? You would give them a wide berth, and that's actually what this type of learning does. And analogy-based learning was one of the oldest and most widely used types of machine learning. But one application these days that it's very important and we're all familiar with is recommender systems. Right? These are the systems that every e-commerce site worth its salt uses to suggest products you might want to buy based on the products that you've bought before. And a famous example of this, of course, is Netflix. 3/4 of the movies that people watch on Netflix come from the recommender system. This is how important this is to their business. And on Amazon, 1/3 of what people buy comes from their recommender system. So how does this work? Well, the idea is very simple, is how can I predict whether you will like a particular movie or not so that I can recommend it to you? What I do is I look for people who have similar tastes to yours. And the way I figure out whether they have similar tastes to yours is, of course, that they've given similar ratings. So if someone gave high ratings to the movies that you give high ratings and low ratings to the movies that you give low ratings, and now there's a new movie that they just gave 5 stars to but you haven't seen yet, then I guess that maybe you like that movie and I recommend it to you. Okay. So to summarize, we've seen that there are 5 main schools of thought in machine learning, what I call the 5 tribes of machine learning. Each one of them has a problem that it's really focused on over the decades and has solved very well. For symbolists, it's the problem of discovering rules that you can compose in arbitrary ways, and their solution is inverse deduction. For connectionists, it's the credit assignment problem, and their solution is backprop. For the evolutionaries, what they can do is discover structure, right? The evolutionaries just tweak the weights on an existing structure, but the evolutionaries can actually come up with that structure using genetic programming. For the Bayesians, the crucial problem is uncertainty. How do you deal with uncertainty? And their answer to that is probabilistic inference. And finally, the analogizers, by reasoning by similarity, they can learn from many fewer examples than anybody else. For example, from just 2, you can actually form a frontier. Or you can generalize, across very different things, like generalizing from the solar system to the atom, which is how Niels Bohr came up with the first quantum mechanical theory by saying, well, the nucleus is like the sun and the electrons are like the planets and so on. But really, so this is the state of the art today. But I would say that what we really need is a single algorithm that solves all 5 of these problems. Precisely because each of these problems is real. No single approach actually has everything that we need. And a bunch of us have been working on this for a while. We've made a lot of progress. We're getting close to what you might call a grand unified theory of machine learning. In the same way that the standard model is a grand unified theory of physics and, the central dogma is a grand unified theory of biology and so on. But I think we still have a ways to go. And my guess is that we're going to need ideas that are beyond what I've described here. And in a way, paradoxically, it's perhaps people who are not in the field who will most be able to have those ideas. Because again, When you're in a field, you start to thinking along the lines of that paradigm, and often you don't see the other things that you could be doing. In fact, one of my goals in writing this book was to get other people outside machine learning to start thinking about these problems and maybe have ideas. So if you do have an idea, please let me know so I can publish it. So let me just conclude by mentioning some of the so we've already seen some of the major applications of machine learning today, from recommender systems to spam filtering, to speech recognition and image recognition and so on. But let me mention some of the things that we are working on in the research labs and that I think will be possible once we have, the next stage of machine learning. One of them is home robots. Right? We would all like to have robots that, cook, do the dishes, make the beds, maybe even, look after the children. And this, I think, we don't have this yet because it can't be done without machine learning, and it's beyond what today's machine learning algorithms can do, but it won't be beyond, for example, this, unified learning algorithm that I just talked about. Another one is something that all the major tech companies are working on, which is what I would really like to do when I'm on the web is not type keywords and get back pages, is to ask questions and get back answers. But in order to do that, I need to represent the knowledge, that's basically in text in web pages in a way that the computers can understand, and then deal with the fact that it's very messy and incomplete and contradictory. And again, I think this is something that we need the next generation of machine learning to do. Here's another one, perhaps the most important one, and that's curing cancer. Medical diagnosis is actually one of the killer apps of machine learning. I can take, a database of 1,000 patients and run a very simple learning algorithm on it for 10 seconds, and it learns to diagnose, for example, lung cancer or breast cancer from x-rays better than people who spent years and years in med school. Or, if I want to recommend a drug, right, it's a little bit like recommending, a movie or a book. But the problem with cancer that makes it much harder is that cancer is not one disease. Everybody's cancer is different, and the same cancer mutates as you go along. So it's very unlikely that there will ever be a single drug that cures cancer. The cure for cancer is a machine learning system that looks at the genome of the patient, the mutations in the tumor, the patient's medical history, and so on, and recommends the specific drug that will kill that cancer without harming the patient's healthy cells. And for that, we need to build models of how the cell works, how gene regulation works. And, there's a lot of people working on this today, and I think we will get there, but it's, it won't happen overnight. And finally, apropos of recommender systems, what we have today is each company has its different recommender system based on the data from you that it has access to. It has a very narrow picture of you. So, Netflix, predicts your movie tastes based on your movie ratings. Amazon predicts what you want to buy based on what you've done there. Facebook has a model of you to predict what updates to show you. Twitter has one for tweets and so on and so forth. But this is really not very satisfying. What I would really like to have as a consumer is a 360-degree recommender system that learns from all the data that I've ever generated and then helps me with, it assists me with all the decisions that I have to make at every stage of my life. Not just finding things to buy, but finding jobs, deciding where to go to college, finding mates, right? Dating is actually one of the biggest applications of machine learning these days. A third of all marriages start on the internet, and the matchmakers are machine learning algorithms. So there are actually children alive today that wouldn't have been born if not for machine learning. Okay? But the truth is, this is a very hard problem. You can't really you can't predict whether people are compatible from just their profiles. But if you have access to all their data, if you have a really complete picture of them, then you can do a much better job. Not just for dating, but for all sorts of things. So, more about all of this in the book that you have on your table. I hope that you enjoy it, and I'll take questions.
So the first question is always difficult, especially for evolutionary makers of algorithms. So let's go straight to the second question. Just wait for the mic, and if you could say who you are and where you're from.
Hi, I'm Peter Miskowicz with JLL. Excellent presentation, Pedro. In terms of machine learning, what is your forecast in terms of workforce, algorithmic replacement of human beings? Lots of discussions from Brookings, MIT, and elsewhere. And what are your thoughts there?
Yeah, I mean, this is a huge debate that's going on right now, right? It's like, what is machine learning going to do to the world of work? And a lot of people are concerned that machine learning is going to lead to massive job losses, right? There's been these predictions that, half of all jobs will disappear in the next 10 years or such. I think, I mean, there's a lot to say, but let me just mention a couple of key points. Some jobs, I think, are going to disappear. Like, for example, I think truck drivers have a reason to be worried. And, truck driver is the most frequent profession in 30 of the US 50 states. However, I think what's going to happen with most jobs is not that they're going to disappear, is that the way they are done will change. It's really not, I mean, the question that I think we should all be asking ourselves is, what in my job can be automated? And what can I do on top of that once it's automated? I can probably automate the boring parts and actually then get on to doing the things that I wish that I had the time to do. So in a way, the way to keep your job safe is to automate it yourself. And here's, I think, a very good example of this. Computer chess, right? So, at one point, Deep Blue beat Kasparov, and now computers are the best chess players in the world, right? Actually wrong. The best chess players in the world today are not computers. They are teams of humans and computers. A team of a human and a computer can actually beat a computer precisely because humans and computers have different strengths and weaknesses. So this, I think, is the way to think about it. Right? It's like automation is like, it's like having a horse, right? If you have a horse, you don't try to outrun the horse. You ride the horse. And as a result, you go farther. So I think this is the way that we should be thinking about how machine learning is going to impact work.
Okay, thank you. Time for one more question. Lady here. I won't ask if you're a symbolist or a connectionist.
Thank you. Hadley Lord with Herman Miller. I've been reading a lot lately about how algorithms are not without bias.
And your name is?
Hadley Lord.
From?
Herman Miller.
Great.
Thank you. Yeah. I've been reading a lot lately about how algorithms are not without bias. So it's been talked about specifically around Facebook and the way that they're using those algorithms to recommend things based off of your activity that might be the most important to you, but that those leave out things that maybe are important for you to know, that maybe they wouldn't predict based off your past behavior. As you start thinking about these different algorithms and creating of a master algorithm, does that kind of increase a specific point of view or bias towards a certain solution versus right now, if there's different types of algorithms, did those algorithms then have different types of bias so that you're getting a little bit more of a broader bias, I guess you could say?
Yeah, so this is another very salient issue these days. I think it's very important to make a distinction between ordinary programmed algorithms that somebody wrote down and learning algorithms. A program algorithm is basically just what you told the computer to do. So it inherits all of your biases. A learning algorithm is actually a very different beast in the sense that the learning algorithm itself, the biases it has are just very general things, like, for example, reason by analogy, like I described here. It actually doesn't say anything in particular about any specific problem. That only happens when you apply that algorithm to data. So in a way, in machine learning, the biggest source of biases are not the algorithm itself. It's the data that you train the algorithm on, and it's how the data scientists use the algorithm. So, we need to, one of the important things that I think needs to happen, and that's part of why we all need to be aware of machine learning, is that we need to be able to scrutinize what these algorithms are giving us in order that we can trust them. And we can say, why did you recommend this to me? Or actually, that was a mistake. You should have recommended that. Or we should be able to tell them, this is the kind of thing that I want you to do for me. What happens today is that the learning algorithms, they're running under the hood. You actually don't, it's a complete black box to us. And what they're actually doing is they are serving the goals of the company that produced the algorithm. Like, Google is trying to maximize the click-through rate on their ads. And Facebook is trying to, keep you, it's trying to be sticky. So I think we all, it's like driving a car, right? Only engineers and mechanics need to understand, how the engine works, but everybody needs to know where the steering wheel and the pedals are. We all need to know where the steering wheel and the pedals of the learning algorithms are. And they have the equivalent of that. It's just that most people aren't aware of that today. Yeah.
Pedro, thank you very much. I've got this irresistible vision of corporate robots in 40 years' time having to attend an unconscious bias workshop.
I bet you they will.
That may happen. I think a wonderful start to the conference. You have opened up a world of thinking from symbolism to analogy. Big thank you to Dr. Pedro Domingos.